we're recording. I can't see whether or not. I guess the smarter thing to do would be. Okay, I believe. All right. I even have it pointing at the right board. Who says I can't learn new things? Okay, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing change that. It is Monday, our happiest day of the week. The last thing that we talked about in lecture were state variables and transfer variables. We were at least somewhat happy with this. Okay. So imagine a piston with a plunger. In the piston is trapped some gas at pressure P, volume V. The plunger has cross-sectional area A. If we take said plunger and drive it down through some displacement dy. We've previously been okay with this idea that force owed to pressure goes as pressure times the area subject to that pressure. Use this term repeatedly over the coming couple weeks, quasi-statically. By this, I just mean that we're going to make the changes gradually enough that I'm never so far out of equilibrium that I couldn't go back without any penalty. Is that all right? So I'm just going to slowly, gradually work my way out of the room, and you won't even notice I'm gone. Right? So we're going to go through a quasi-static compression. I want to say minus. So in that case, our work done on the gas, or at least an incremental bit of work done on the gas, is going to go as F dotted with ds is going to go as minus F j hat dotted with dy. J hat is just going to be minus F dy. Winds up being minus PA dy. Yay? But ADY is what? It's just an incremental bit of volume, right? So then we can say that the work done on the gas is going to be minus PdV. We're happy? Just to put a finer point on this, if the gas is compressed, then dV is what?
Negative.
dV is less than 0, it's negative, right? And so what does that say about the work done on the gas?
It's positive.
Work done on the gas is then positive, yeah? If the gas is expanded, then dV is greater than 0, and corresponding to this, we have that the incremental bit of work done on the gas in this case is negative. It's all right? If dW on the gas is minus PdV, then the work done on the gas in going from V1 to V2 is just going to be the integral from V1 to V2 of PdV. So far, so good. We're happy-ish. Okay. Last time we met, we talked about our state and our transfer variables. And do you guys remember which category work fell under?
It's not a state.
It is not state, so it's transfer, right? So I think that we can demonstrate this in a somewhat practical fashion. If we have V1, V2, and P1 and P2, so let's say that we begin at V1, P1, and we want to wind up at V2, P2. I can imagine a few different paths that would carry me there. So we could imagine compressing at a constant volume, and then we could imagine compressing at a constant pressure, and then we could imagine increasing the pressure at a constant volume. Then, if the work on the gas is integral PdV, how's that manifested here? Well, it's just the area under the curve, right? Yay? we could imagine instead doing something similar. But this time, maybe we take the opposite. We go thusly. Yay. Same starting point, same ending point, different results, right? Our transfer variables are definitely path dependent. At least on our PV diagrams. Yay enough? Okay. Then remember pressure, volume, those were state variables, right? And so from one state to another state, right, our transfer variables can carry us. But the path we took actually does matter here. So we're going to examine some special cases of our ideal gas law. So we had that PV went as nRT, or PV equals NKBT. Yeah. And so we're going to look at some special cases of going from one state to another state. We're also going to make use of our first law of thermodynamics. So our first law of thermodynamics is really kind of a statement of conservation of energy. So we're going to say that delta E internal, this is probably the only time all semester I'll write out internal, is going to equal Q plus the W on the gas. What is Q in this context? Heat. Heat, right? So if we have some gas, and what is delta anything? Change in, right? So the change in the internal energy is equal to the heat, right, passing through boundaries, plus whatever work is done on the gas. And so you can see that if you do work on the gas, you would expect that the internal energy should go up, yeah? If you add energy as heat to the gas, again, you expect its internal energy to go up. Yeah? So the sign of this makes sense. Because I'm somewhat lazy, I'm sure at some point this semester I'll just write Q plus W. And from context, I'm going to expect that that you're going to remember that that's the work done on the gas. Yeah? Remember, the work done by the gas is going to be the negative of that. So if we were writing this equation in terms of the work done by the gas, we would say delta E internal is equal to Q minus the W by gas. Yeah? Okay. So
Just a quick question, why the Q it's always positive? Do we ever have work minus Q or something like that?
well, so if energy was flowing out of the gas's heat, then this value is negative. So this value of Q could be negative,
Or it
right?
could be negative.
Yeah. Yeah, if the gas is expelling energy as heat, if instead of this, what we had was this, then the value is negative, right?
Okay,
At least as far as that equation is concerned. So far, so good.
Why we can add Q and add W? Do they have the same unit?
They do. What is heat again?
Energy.
It is the transfer of energy, right? So heat has units of energy. So too does work, right? We're happy? Okay. So
Is the unit a joule?
any unit of energy is valid. So you
But how many units we have? I only know joule.
so we could use
We can-
calories, ergs.
Calories,
We could use a dyne centimeter. I mean, there's,
Dyne centimeter? What's
dyne?
that? What's that?
dyne is just a unit of force. So. Sir.
So if the container if the container's not a cylinder,
Doesn't matter.
you've told me that before, but I don't see how, because the area would be changing as you push it down, so I don't get how.
But note that we did this for dy, right? And so cross-sectional area over some very, very small dy. What I am building into that is that the cross-sectional area isn't changing dramatically over dy.
Would it be a different derivation if it was a
Be
sphere?
harder derivation.
But you would
You'd
still end up
want
with
you'd
PDE.
want a full-on better person than me.
But you'd still end up with PDV?
Yeah. You would. I would be cowering in the corner. Okay, so we could incrementalize this, right? I could say that dE internal is going to be dQ plus dW on the gas. Yay? This is really a statement of conservation of energy, right? That, if you account for all the things that have happened, right? Energy that is entering or leaving the gas's heat, energy that is entering or leaving by virtue of work done on the gas, that has to show up in a change in the internal energy. That makes sense? There's no magic in this, right? Okay. Then, one thing that this leads us to is that for a cyclic process, that delta E internal is going to wind up being 0. If you take it all the way back to the point where it started, there's the system is reset, right? And so in that case, we have part Q has to be minus W. And I'll hold out remembering to write on gas as long as I can, but I'm going to forget.
It's internal energy the same as thermal energy, or thermal energy is totally different?
The internal energy is our kind of stored energy of the
System.
gas, right? And so it's and the only means of storing in the ideal gas is in the translational kinetic energy. As we go further, we'll also be able to throw some in rotational and vibrational bins, but not yet. So let's look at a couple of very specific cases. The first case is going to be an adiabatic process. For an adiabat, we are not going to allow energy into or out of the system as heat. And so how does our first law simplify in that case? Delta E internal is just the work done on the gas. We could look at our isobaric process, isobar. For an isobaric process, the pressure is held fixed. And in that case, what do I know about the work done?
The pressure is,
Final minus V initial.
Yeah, so if the pressure is fixed, it can come out of the integral. And I just have P integral dV from V1 to V2, right? And so yay. We could look at our isochoric, our isovolumetric. And in this case, what's held fixed? Volume is. If V is held fixed, what happens?
work is 0.
The work is 0. And so what does that say about first law? Delta E internal is just equal to Q. Yay? So far, so good.
Wait, but couldn't it be that the volume, like, couldn't it be that the gas is doing work on the surface and the environment's doing work back?
It's enclosed, isn't it,
So
from the environment?
it can be in a container, right? But if there is no change in position, right? If there is no kind coming back, where is our earlier statement? If there's no ds, right, there's no dw. Yeah? So I can lean against the wall, right? Not doing any work.
Oh, I see, yeah.
Does that make sense? So I didn't space this out very well, I apologize. We could look at our isothermal process. What's held fixed in our isotherm? Temperature, right? So but looking at our ideal gas law, notice by the way what we've done, right? Assuming that we're dealing with an enclosed system such that gas isn't entering or leaving, n is always constant. So we've just in turn picked on P, V, and now T as things we're holding fixed. So now we're holding T fixed, but that means the whole right side of these equations is fixed, right? And so that means that P times V is also a constant. Does that make sense? So if we begin with PV equals nRT, then we can say that work minus integral PdV from V1 to V2. Well, how can I write P?
F over A, and then
Just write it as
nRT over V.
nRT over V, right? Hooray. But nRT is constant, right? And so I have the integral of dv over v, which looks like what? ln of v. So we can write this as minus nRT ln of v2 over v1 yay. Does that work for you guys?
Can I ask, what's in front of the dependency, the Ln or,
A natural log, yeah.
oh, natural log, okay.
Right, because I could take this to integral dv over v is so far so good. Then I shouldn't put this right here, but I'm going to because I've already done it. Even though I have all these words to write on it, I think still living in the trauma of the past and
Planetarium.
conserving as much board space as I can. That's not very good. But Thankfully, I have a forgiving audience. I say, as you're all shooting me daggers with your eyes. But I want to look at a pair of different isotherms. What does an isotherm look like on a PV diagram?
Do you mean the physical shape of the lines, or?
Yeah. We have that PV equals nRT. I'm telling you that isotherm means what?
Constant temperature?
Constant temperature. So P times V equals a constant. What does P against V look like?
Like hyperbola?
Well, does it stand to reason that P is at least proportional to 1 over V? So it looks something like a 1 over X plot, right? Okay, in this first quadrant. It looks a little bit like what I drew. Yeah?
Yeah.
Okay. So what I intend is for these to be two different isotherms, right? So two different isotherms for the same gas, what does that mean?
Different temperature?
Different temperature. Which of those has a bigger temperature?
Upper one?
If P times V looks like N times R times T, then the bigger the product of P times V, the bigger the temperature, yeah? And so the further, the bigger the radius from this origin to a point on the isotherm, right? To the nearest point on the isotherm, let's say, the bigger the temperature, yeah? We're happy-ish. Then we have our initial state, we have our final state. I'm going to give myself 3 different possible final states on the higher temperature isotherm. And
The triangle is just prime, right?
yes, sir.
Or-
Does that stand to reason? So if we're talking about an ideal monatomic gas, something like helium, right? Let's go with the noble gases. Helium, neon, argon, there's others, but let's start with those. Then any energy I add to this gas, what happens to it? Can it go to making the molecules sit further apart?
No, because you have the same volume.
It can't go to making the molecules further apart because it's monatomic. These aren't molecules. Yeah? I'm not talking about a case like this where maybe we have two oxygens that are bound together. Maybe one way of adding energy could be to get them to change how far apart they sit from one another. That won't work here because these are just individual particles. Yeah? So where does any energy I add go? This goes to the question that Lorenzo asked just a second ago. Goes to translational kinetic energy. Right? It's the only place it could go. So E internal in this case is going to look like what?
P plus, wait, there is no work being done.
It's just going to be the total translational kinetic energy. Yeah? If any energy I add to the gas, it's ideal and monatomic, goes into giving the gas translational kinetic energy, then the total internal energy, this is a little cyclic or self-referential maybe. That's because but the power of suggestion. But here, right, it's the touch self-referential. But if the only place for me to put input energy for a gas is translational kinetic energy, then the total internal energy has to be the total translational kinetic energy.
Does that just mean the particle moves faster in the air? Or, where it's at? It's faster in its movement?
VRMS is definitely different, right?
Mm-hmm.
So the speed of the particle on average is different.
So how fast would it go? Would it stop at the speed of light or right before it?
Oh, see, there we have to be careful. As far as we know, nothing with mass
Can travel at
could travel at the speed of light.
Right.
So we'd have to be a little careful about what it means to add energy once you start talking about very, very, very high energies.
So do the particles just dissipate at a certain speed, or what happens like right before the speed of light, or like what happens when they reach their speed?
We are going to get to what happens as you try. So we'll talk about relativistic kinetic energy. But it's not, Newton's description here, or Newtonian physics description here, works really well at our slow speeds. It doesn't work so well at relativistic speeds. So we'll have to be a little more careful about what we mean. And this is maybe as good a time as any to talk about this, but towards the end of the term, what we're going to get to is this idea of correspondence. And by this, what I'm going to insist upon is that anything that has worked well for us before, if we want to replace that with a so-called better idea, better theory, that better theory had better be able to also explain things that the old theory could explain. Mm. Just because the old theory couldn't explain this new thing, you're not going to throw the old theory out just because there's some new theory that can explain this new thing, but it wouldn't explain the old thing. And so one of the things that...
So you have to find out what works with the pre-existing theory.
One of the things that you're going to have to see for relativistic kinetic energy, before we're going to be able to put any faith in it whatsoever, is that it gives the same answer as Newtonian physics would, classical physics would, in the same regime of our very slow lives. Is that all right? I usually have a worksheet for special relativity, and one of the questions that I included last year is kind of a somewhat stock and standard so-called paradox. It's not actually a paradox. The paradox comes from applying classical physics, but one of the things I tacked on at the end involves relativity in an oven, and that gets a little hard.
You say oven?
Oven.
Like a kitchen oven?
Sure, could be.
That's very interesting.
So I think the way I framed it was using Girl Scout cookies, licensed print money.
Nice.
I cannot walk by a table of Girl Scout cookies without buying a box of cookies.
Are you saying the internal energy of any monatomic gas is always just the total kinetic energy?
Of the gas, yeah.
That doesn't make any sense.
Why not?
There's-
Are you okay up to here? Any energy you add has to go into translational kinetic energy?
Oh, well, I was just thinking, like, if you change the pressure around it, then there could be work done on it.
So what I'm asking is, are you okay that any energy I add to an ideal monatomic gas has to go into translational kinetic energy?
I don't know why that would be.
Well, so remember our very restrictive rules that the only way that the particles interact is through collisions. There's no forces in between collisions. So that rules out stuff like electric force, magnetic force. Right. So in that case, is there any way for me to store potential energy?
No.
Okay, so kinds of translational, the kinds of kinetic energy are translational, vibrational, and rotational, yeah?
I see.
The vibrational we're going to exclude because since it's monatomic, we don't really have this ability to oscillate about some bond. And the rotational, we're kind of assuming that that the atom doesn't have a face, right? Is that the vegetarian version, friendly version, right? My wife used to tell me if it doesn't have a face, it's okay for me to eat it. But don't get me in trouble. This is being recorded. So the atom doesn't have a face and a backside, right? So if it is undergoing rotation, I don't know what it is, right?
Okay, but
It's a point in our model. So the only way of storing energy then is for this to have
there can still
translation.
be a change, and there can still be heat added to it and work on the gas done. to
Sure,
change
but
it. It's
anything
all
that
translational
happens
kinetic energy.
is going to get dumped into translational kinetic energy. Think of it like piggy banks, right? And one of the piggy banks, in this case, is getting all the energy, or all the money. So then if that's the case, right, if any energy you add is going into translational kinetic energy, then the total amount of energy is the total amount of translational kinetic energy, right? That works? Okay. So then, in that case, going back, I don't know, a couple days now, we had said that KE total translational was 3/2 nRT.